So this is our channel of the STFT filter bank. Signal comes in, gets heterodyne down, low pass by W, and downsampled by R. That's what it does. So in this diagram, you can just apply basic seat-of-the-pants signal processing to see what this window has to be in order to be a good anti-aliasing filter. Right? If we're going to downsample by R, then this window needs to cut off at half the new sampling frequency, right? So so basically pi over R is our new cutoff, right? So this W needs to be a decent low-pass filter that rejects spectral energy above pi over R, because we're going to downsample, and you don't want to alias. So that's what you want out of this window. And what does it take to get that? So here's the diagram of that. So this should be qualitative. You want your main lobe to be down into the side lobes by pi over R. And if you make a table of this, and if you say that the window main lobe width is just the distance to the first zero crossing, and you look at the Blackman-Harris families, then this is what you get. You find that for the rectangular window, you have to, you can only hop half of the window length, because it's half the window length that gives you a frame rate whose half equals the first zero crossing of the main lobe. And for the generalized hamming, it's only you can only jump a quarter of the main lobe. You have to go with 75% overlap. So this is what I was alluding to earlier when I was telling you that if you just want constant overlap bad, you can jump the whole window for a rectangular. You can jump half the window for anything in the generalized hamming family, and so on. But if you want a good anti-aliasing filter, which you will want if you're doing advanced processing of the spectrum, then you need to drop back a factor of 2 there. You need to slow down and go half as fast through the spectrogram in order that your window transform is behaving as a decent anti-aliasing filter. And so the right question to ask is, how can this other stuff work? I mean, if you are jumping too far, it means that half this main lobe is aliasing. I think I have a picture of that. Yeah. So here's a depiction of the main lobe, and here's a depiction of pi over R, and 2 pi over R is where we used to be putting our first zero crossing. In other words, for the other, for just constant overlap bad, this is sufficient, and it's kind of a Nyquist criterion here for these zeros. That means that in the output of the filter bank, all of this information is aliased. So look how much stuff is aliased. Basically, the outer half of the main lobe aliases down onto the inner half of the main lobe. So it's a very heavily aliased signal. And so what happens to that aliasing when you don't, when you jump, a full window for the rectangle, you jump half a window for Blackman-Harris, or for hamming, generalized hamming? Well, the answer is it gets canceled. And so now a good check question right now is, how exactly does the aliasing cancel? and that's a good exercise, and that's a harder exercise, I think, than the bow tie question. But that's a good thing to do, is to try to see if you can see, first of all, where is that aliasing exactly in the tiny? I mean, what exactly is aliasing, and how does it get canceled? And actually, I think I may have misspoke. Yeah, I did misspeak. The aliasing cancellation is in the frequency domain in this case, because this is the filter bank summation point of view, and this aliasing is frequency domain aliasing, and it gets canceled. And so, and the important point to note and emphasize and say now and next time is that aliasing cancellation gets disrupted when you start doing things to the spectrum, when you start processing it, when you start isolating spectral regions, doing virtual filtering and processing. The aliasing cancellation is coming from adjacent channels. And if you change the gain of those channels, then you lose your aliasing cancellation. So when you're relying on aliasing cancellation, you're not able to do modifications without getting more artifacts. That's the bottom line. And this, by the way, we had a student who looked hard at the question of processing MPEG audio in the compressed domain. And the bottom line was, it didn't go very far because of all the aliasing cancellation that was inherent in the MPEG audio format. When you've got aliasing cancellation, you don't have freedom to modify.